How are we doing? I think this is as full as it's gonna get, so we may as well start. It's my pleasure today to welcome Andre Longtin to the Neurotheory.World forums. Andre is probably most well known for stochastic resonance and for his electrical fish research. He's a physicist who got his PhD in Montreal in 1989, and after only 2 years of postdoc, I think, became an assistant professor in Ottawa, where he has been since. He's been a full professor since 2002 there. So he's got a long career on complex system, nonlinear system, and electric fish, as I said already, behind himself, and more to come. He's just recently won a prize for the NERC prize. What is it called, Andre? The NERC prize in Canada?
NSERC Brockhouse, yeah.
For interdisciplinary research. And we're quite happy to have him here today from the north of Canada. I suppose not the real north, but from the boonies, from the quarantine to Oxford and to the world. Without further ado, the floor is yours, Andre. Thanks for coming.
Okay, thank you very much. Thanks for giving me the opportunity, Tim, and others there at Oxford. I'm talking to you out here from we're about an hour and a half north of Ottawa. So we just had a snowstorm. Winter still raging up here, but it's beautiful, and no bugs, no COVIDs around here, it seems, so far. So I'm going to be talking about some recent work done by 4 people in my group. Part of it is in collaboration as well, and it all has to do with brain rhythm circuitry, how you can understand a specific property of it called burstiness, because the rhythms are not sustained, they're bursty. And also, how do you infer those circuits in the first place, using some modeling techniques and some inference techniques. So the outline is following. So I'm going to talk about, for part 1, beta gamma rhythms. So what regime are we looking at generally from a dynamics point of view, and why are they bursty? And this is work done by my PhD student, Arthur Pawanwe. And the second part is heading towards trying to estimate the properties, the models for these systems from microscopic data. And in order to do that, that's going to be part 3, we need some kind of mesoscopic description of the microscopic data. And that will be part 2, one effort we did in that direction. And there's another effort done by another group, by Wolfram's group in Lausanne, which will be the basis for what we're doing in part 3, which is actually inferring the circuitry. So 2 classes of micro to meso models. Okay, so, all right. So brain rhythms, of course, they're ongoing voltage fluctuations in neuron populations. You can record them with EEGs or with local field potentials. They occur in different frequency bands. I'm going to be focusing mainly on gamma, but what I'm saying applies as well to beta. And these rhythms, of course, play major roles in a variety of brain mechanisms, such as communication between areas, memory, attention, and motor control, especially for the beta rhythms. And the statistics of these rhythms can be altered in brain disorders, such as Parkinson's and epilepsy. And by statistics, I mean not only like what's the frequency and amplitude content, but the whole trajectory, whether things start and stop in random ways or non-random ways. So there, just as a background, so we have 2 types of neurons we're going to be looking at, excitatory and inhibitory. But you can also have, let's say, gamma rhythms arise mainly from synchronization of I neurons through the ing mechanism, and the E's just kind of follow their output. Or you can get a back and forth going between the E's and the I's, referred to as the ping mechanism. That's the one I'll focus more on throughout the whole talk. These rhythms are autonomous, and they can be induced by or altered by stimulation. And of course, there's been lots of deterministic modeling of these rhythms, dating back to Jack Cowan and Hugh Wilson's work in the late 60s. And but there have been more efforts in recent years to understand the stochasticity of these rhythms, because they are really stochastic. So this is data from visual cortex of macaque from Zing's group. At the top, you see a wake monkey amplitude. This is the LFP. And then at the bottom, you see the spectrogram. And what I want you to pay attention to is that the spectral power is not consistent. It kind of shifts around in bands and in duration as well. So those gray blocks show you these epochs where the rhythm seems to be more sustained than others. And those are called bursts, gamma bursts. Now, if you do an analysis via Fourier of the amplitude and the phase, you'll get a range of frequencies with a bump somewhere, and then you call it, for example, gamma. The bump can be pretty broad. And then you look at the phase, and it's all over the place, okay? Now, what Zing did is to consider the durations of the bursts. So the top plot here, I don't know if you can see my cursor, but you have the frequency content of the bursts as a function of the duration of the bursts on the x-axis. And you can take the marginal on the below here and just look at the distribution of the burst durations. So you see that some bursts go from, I don't know, around 30 milliseconds all the way up to, past 250, 300 milliseconds. So they vary quite a bit. The gamma oscillations in vivo appear thus as short epochs or gamma bursts, and the occurrence and the duration seem to be random variables, which is not too surprising given how noisy the brain is. The mean burst duration is between 65 and 150 for that prep. The joint distribution of burst duration and peak frequency can be some signature for a particular task or brain state. The deviations from the healthy burst duration range can signify that some pathology going on. And this observation, along with others, has led to the view that gamma activity is maybe nothing more than filtered noise generated by a recurrent EI network. And the bursts have also been suggested to be important communication events by Palmagiano and others, and Fred Wolf and Theo Geisel's group. Okay, I'm gonna check in here. So everyone's still around? Okay, it just feels weird here, like I'm talking to myself. Okay. You can hear me?
We can see you, and we can also see your pointer, just so you know.
All right, good. Okay, now we're gonna be looking now to describe these bursts. What's a theory of bursts? And to look at the bursts is really to look at the long time scale, so the envelope of the rhythm. So it would be nice if you had a model that can give rise to the statistics of that envelope and the phase. We're going to do that in the ping model. And the goal is to look at mean burst duration and burst frequency. Burst peak frequency, you can calculate the mean as well. And to find the dynamical regimes where the burst statistics match the experiments. And ultimately be looking for some theoretical expression of the burst duration in terms of all the parameters, single cell and the network parameters. In particular, you can frame this as a first passage time problem. How long does it take for the envelope to go from one point, like low, up to a high point and back down? So from a stochastic process point of view, this has the flavor of a first passage time problem. and I'll explain what that is. So the model that we were looking at is a stochastic version of the 1972 Wilson-Cowan model, done later on in Jack Cowan's group by Wallace and Benayoun and others. And it looks like those two first equations here. So one for the average E activity and one for the average I activity. So you have the decays and the self-limitation, but then you have these noise terms that are dependent also on the states and the dependent on the number of neurons. So the noises, these are finite size effects, noises. So if you were to send the values of n to infinity, you'd get rid of the noises in this description. And in the limit where n goes to infinity, you recover the classic Wilson-Cowan system. And this is related to two-state neuron models as well, in the beautiful work that Wallace and others have done. The important thing is that this is still nonlinear, okay, because f is the firing function, as a function of the input s. And here's the network. So you have E to E, I to I, E to I, and I to E. And you have two independent Gaussian noises. And this system is going to have complex conjugate eigenvalues, and we're going to focus on the situation where that nu here is positive, where you're below the Hopf bifurcation that this system has. So sorry for this busy slide. There'll be a few. I'm not going to go through all the details, but from this, just to recall, for those of you not aware of this formalism, you can do the linear noise approximation, where you separate out E into some local field potential with some scaling with the size of the system. And then you get these two equations, and these are the main ones. And notice that these equations are now purely linear. And they have additive noise. The noise is no longer multiplicative, it's actually additive. So that means that from the point of view of the dynamics here, all this is a two-dimensional linear filter driven by noise. In other words, this is a two-dimensional Ornstein-Uhlenbeck process in some coordinate system. Now you can look at the LFP properties, you can look at the ratio of amplitudes and the phase differences, and you can then say, okay, I'm going to hunt for the slow time scale, so Z. So you'll express the local field potential as a function of a slow amplitude and a phase. You can do this with Hilbert transforms as well, of course, but it's pretty hard to do that on the theory here. We're looking for dynamics of Z and cosine and theta. So you reduce these fast dynamics to these slower dynamics. Not going to take you through this, but this is just to convince you that, with the linearization, every element of the matrix, A11, 12, 21, and 22, has all the parameters in there of your original model. We'll be working only with these four matrix elements, but all the parameters are in here. And of course, it's technically a bit tricky to find out, how do I change A12? Well, I need to change these parameters. How do I change these? Well, if you change any parameter, you're going to change the value of the fixed points through the nonlinear, nonlinear equations you have to solve to get the fixed point in the first place. So it's, it's not smooth. You can't see it directly, what happens when you change a parameter, but you have some analytical handle on the whole thing in principle. So the regime we're going to look at is the asynchronous activity. So just near but below the onset of synchrony, so just near the Hopf, where there's no deterministic limit cycle, and the rhythm is induced by the noise. That's the important point here. So the rhythm is generated by the noise, synaptic or other. If you turn off the noise, there's no more rhythm. So here's a two-dimensional subspace of the parameter space. I'm just looking at the connectivities to give you an idea here. As you're increasing the E to E connection in this space, you're going to cross this red boundary, which is the Hopf boundary. Above the boundary, you have high synchrony. So you see the fast voltage here is highly synchronized. This could be like, epileptic seizure. If this were a good model for that, it isn't yet, but to give you an idea, this is a high synchrony, and the spectrogram is nice big band. And we're going to work in this regime that looks more like Xing and other researchers' data, transient synchrony. And we're going to look at 4 points as you're approaching this boundary. This boundary has also been shown by Belén San Cristobal and Jordi Garcia Ojalvo in Barcelona to be relevant to some of the waves they've seen in their recordings a few years ago. So this transient synchrony regime is gaining more and more momentum in terms of a possible area to look at for rhythms. Of course, Nicolas Brunel and Vincent Hakim have worked a lot of this out and been proposing this for almost 2 decades now. Okay, now the method to get this is called the stochastic averaging method, and that would take too long to explain how that works. I refer you to this paper here, where they show that method. It's an approximate method for getting slow equations from fast equations when there's noise. Also, the work by Cindy Greenwood and colleagues here, where they did a similar decomposition back in 2015. What we did is we included more of the parameters all the way and did it with the stochastic averaging method. And what you get in the end is this thing. You get an equation for the envelope, an equation for the phase. They're high order terms. We forget about those, but this is the basic lower order terms. And you have all the parameters here. So nu is, these are all the matrix elements. And you saw earlier, all the matrix elements are functions of all the system parameters. But things get pretty simple at this level. You get a diffusion process on a nonlinear drift here for the envelope. So the envelope is drifting according to these dynamics and this driving noise, and the phase just kind of follows. When the envelope goes high, the phase velocity goes, just drops. So you can get some insight on what's going on with this. And what we're interested in is the distribution of the probability of Z. So P of Z you can compute directly from the Fokker-Planck equation. You can get P of Z. And this is something that you could compare in principle to experiments. You can see what's the distribution of your amplitude that you extract from Hilbert transform analysis. The peak of this thing depends on the quantity R, which is the noise divided by nu, which is the eigenvalue, and the real part. And in fact, the whole problem of envelopes for the Wilson-Cowan model with noise is really governed by only one meta parameter, which is this thing. You see it shows up in this part and this part, right? And that parameter is the one that I'm going to be varying, going from here to here to here to here. Okay, so as you change that parameter, you can look at the distributions. So this is going from getting closer, 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 and closer. And what you notice is the bursts are getting longer as you're approaching the Hopf boundary. So this is a distribution of the burst durations. So the burst durations here are longer than in this case, okay?
Sorry, can I ask a question?
Of course.
How you define a start and the end of the burst? I think burst duration definition is not straightforward. I think you agree,
Absolutely.
Yes? How you do?
So what we use a technique that's been already proposed in the literature, where you actually have to put the bar up a little bit, your threshold up a little bit as you're increasing the parameter here, as you're getting closer.
Yeah, but little bit, I mean mathematically, how you define, or do you define that? Why it is important for me, for example, the question come in general, any oscillation or bursting activity is tonic or phasic. And therefore, when you ask it is tonic activity maybe, or it is only phasic activity, or is sum of two, and therefore definition of the start and the end, I think is very critical and should be mathematically defined.
It is. I don't have time to go into the details right now. It's in the paper. What you have to do is to impose a criterion where you have to have a certain number of cycles. Like we put actually a minimum of 2 cycles of the fast rhythm to separate out the beginning of 2 bursts, because this is a first order SDE with Gaussian white noise. You can get an infinite crossing rate of the threshold. So
thank you.
Yeah, so then you have to you can space it out. So you can put some extra criteria on there to make sure that you don't get these multiple crossings of your threshold. But we can chat more later for more details.
Yes,
okay.
Interesting. Thank you.
But yeah, it's an important question, and the experimentalists I presented this to also, that's like the first question they asked.
Yes.
Okay, and so now you can actually look at one of these bursts in detail, and so you see, as I just said, you'll get some multiple crossings. Sometimes you got to get rid of these and say they have to be separated by at least 2 cycles to be called a burst. But the duration of the burst, you can go from down to up and then back down, and that will be your burst duration. Now, as we were doing this, a theoretical paper came out on how to do first passage times to the same point, and we're actually almost done that work. It's a lot more involved mathematically, but this is an approximation I'm talking about now, where we actually calculate the burst as like the mean time it takes to go up to a typical maximum plus the time it goes down, and then you can convolve these two. You can add these 2 random numbers, and you get this expression here. B is your threshold, C is the typical maximum, R is that meta parameter, and T is the mean burst duration. So R contains nu and D, that contains all the matrix elements, which contain all the details of the biophysics in there. So it's not completely obvious to say, well, what do I do to my patient to get the bursts back into the right range if it has Parkinson's? You can't just change B here too easily, but you can actually work that out in principle if you think that this is a good model for Parkinson's. It isn't, okay? It's a partial model for Parkinson's. Right, if you look at the burst duration here, red is theory, so green is the numerics. Again, as you're getting closer and closer to the Hopf, you see that it's a pretty good estimate of where the mean burst duration lies. And now you see that in this range here for B and C, you're kind of in the range of the experimental data. So we can look at these joint burst duration peak frequency distributions, and B and C are in a similar range of burst duration between 65 and 130. The frequencies here are a bit higher because looking at peak frequency rather than mean frequency, but believe me, they smell more like the data, which would mean that the system might be in this range here to produce this kind of data. Okay, you're not right up against the Hopf boundary, you're not too far away, but to get the right burst statistics, there's a sweet spot around here. That's one conclusion of this study. Okay, so in summary, this theory of rhythm bursts uses the stochastic average method to produce envelope phase equations. Turns out the coupling is one way from the envelope amplitude over to the phase. And that was already observed in the work of Greenwood in the past, but it's kind of interesting that at that point, the equations are coupled only in one direction. It accounts for many observed rhythm features, and we can identify an optimal region in parameter space that produces these stochastic dynamics in this EI network modeled by the stochastic Wilson-Cowan equations. And doing a stochastic analysis, the mean first passage time allows you to compute some estimates of the burst durations, and their duration increases as you approach the Hopf. Now, the outlook on this work is, to extend this to coupled networks. So because now you have a handle on how to couple these kinds of envelope phase equations with one another and look at phase synchronization. And also we can use the approach perhaps as a guide for therapeutic stimulation. So I'm collaborating with Adam Sachs in Ottawa on this aspect. He's a deep brain stimulator neurosurgeon. We're looking at the gamma bursts, at the beta bursts in Parkinson's patients and seeing if we can make any headway in that direction. So in principle, the theory can guide you to correct faulty rhythms. Of course, the devil is in the detail. You have to have a model that actually makes sense. EI is not enough. The other caveats, yeah, so what if the network is not a simple EI? Still, can the EI be a good effective description of what's going on in multi-population networks? And what about spiking networks? What about the nonlinearity of FI curves? What about realistic synapses? All these, of course, are questions. These are, this is work in prep with Arthur, where we actually coupled two of these systems together. And you can couple the E cells together. So this is a ping system. This is another ping system. So two areas of the brain talking to each other through delayed connections. And voila, you get this whole pile of equations. But it's just that you can get amplitude phase for ping 1, amplitude phase for ping 2, and you can study their coupling. And there's 4 noises in here. So in principle, you can do it. And that's work that's coming up soon. Okay, now I'm going to shift gears a bit and talk about towards estimating these models. What are good models in the first place, and can you estimate them at all? I mean, ideally, you can even imagine some kind of personalized epilepsy model. Okay, so I'm going to talk briefly about some work in that direction, where we're looking at models that go beyond mean field, that take into account the fluctuations. It's based on the spike response formalism that Wolfram developed many years ago with Van Hemmen. And so you have the voltage dynamics, the spike trains, and then you have a hazard rate. And you're looking for a mean field equation for the refractory density, and how that can be derived in terms of the escape rate or Hazen function. So in these models, you don't have a diffusion process. You don't have a white noise and dynamics per se. You have some subthreshold voltage, and as that voltage fluctuates, you evaluate the hazard, the probability it's going to fire as a function of time and the refractory states of the neurons. And you can sum the total activity of these neurons. So the activity is given by that quantity here. Now, if you call Q the proportion of neurons in a refractory state R at time t, well, R is simply the time since the last spike. A of t is the activity, is the sum of all the spike trains together. So n times q times dr is the number of neurons with age in R minus dr in R at time t. And if you multiply that by the hazard rate, that's going to be the number of neurons that fire in the next time step. And that's going to be Poisson statistics, because the intervals are very small. So activity can be obtained through this. Now, this is overview, just a review of first mean field. So if you look at the mean field theory versus full network simulation in the context of all-to-all inhibition, you can look at these raster plots of 50 neurons, and you can pile up the statistics of the firings as a function of time. You get this blue curve here, and it's a pretty fuzzy curve, right? But you can take the mean field, and you're going to get kind of the outline of what's going on in response to this stimulus at the top here. So this is excellent progress, having these kinds of models to get at the mean field dynamics of what's going on. We're going to be looking at inference of models using stochastic versions of this in a few minutes. Okay, so now the question, meanwhile, is can we use mean field theory to predict the emergence of oscillations, but taking full account of the Poisson noise? This is sometimes called second order mean field. So you bring in the fluctuations. So this quantity, the probability of the number of firings I just talked about in interval dt, if you take a Gaussian approximation, you get this plus the square root of this times a Gaussian noise. If you work out the details of this carefully, you can obtain actually a balance equation for the fluxes in and out of this age-structured neuron population, and you get this equation here. Now, the first three terms here are the usual mean field, but notice that now there's an extra term, which is a noisy term, and it's a two-dimensional noise. So it's like Gaussian sheet. So what we're dealing with is a stochastic partial differential equation for the activity of the population. So we're trying to take into account the fluctuations, this term here, around the mean field, which is this stuff here. And there's a boundary condition. They're going to run the show, of course, and very important to keep in track. So the activity now becomes this mean field term plus this extra stochastic term. What do you do with a stochastic PDE? Well, you can go upstairs, in my case, of the mathematicians and talk to them. Or you can get two bright postdocs like Gregory Dumont and Alex Payard to hack away at this and make these approximations. Well, first of all, linear noise approximation. And then you can expand the hazard function to first order, bring in, so I'm just giving you the ideas. Don't the details are in the papers. Okay, so but in the end, you can get a nasty looking system for this first order approximation to the stochastic mean field. And it turns out that you can work out the properties of this thing. You can calculate the activity. You can analytically, you can calculate the power spectrum. Analytically, you can calculate the correlation function directly analytically without having to invert this thing, which is impossible as far as we can tell. And then you get the same three plots I just showed you. And this is the mean field. But notice that the data from the simulations, has this fuzziness here. And that's what we want to get, is the fuzziness. And that's what the stochastic mean field equation, that stochastic PDE, does. It gives you actually the fuzziness at the top. And with that theory, you can calculate a lot of properties of these systems. For example, you can look at gamma oscillations to get back to our earlier topic. You can look at a two-dimensional subspace here with the delay and the connectivity. This is the Hopf boundary. And as you go from here to here, you cross the boundary. There's 3 points here I'm going to show you in a second. Results from those 3 points. So this is the going from the asynchronous regime to the synchronous regime, following what Nicolas did 20 years ago. And you can also calculate the spectrum of this. Here's an example. So the red is the theory. Black is the realizations of the stochastic partial differential equation. And blue is actually the full network spiking activity. So you get very good agreement between all three, I would say. And you get the peak, the gamma frequency, and the harmonics. Okay, so to summarize part 2 here, we have a stochastic PDE for the refractory density, and that predicts the mean and the fluctuations of the activity. So properties of the fluctuations as well as the mean. The delays, no problem including them. They're built into the SRM formalism at the beginning. And it enables analytic computation of the spectral properties. What I didn't show is you can actually use a discretization of that partial differential equation along a characteristic curve. If you remember a PDE course in the past, you probably remember characteristic curves. Well, you can discretize your equation along one of those characteristic curves, and it yields a direct method to simulate finite size effects in the network. It turns out that this is good below and above the bifurcation. Actually, on the previous plot here, this was below the bifurcation. B was at really near the bifurcation, and this is actually above the bifurcation. So you can actually go into the Hopf regime, and but there's noise involved, and you can still have a spectrum that's not going to diverge. Okay, and for the aficionado, I would add these 2 points that you don't need any error minimization method, and the number of neurons is conserved throughout your simulations. But we don't have adaptation in here. It could be done, for example, a quasi-renewal approximation, such as the one devised by Richarneau and Digger and Wolfram. And we have only one population. You could add more. The math is will get pretty lengthy, but it's doable in principle. Okay, now I'm going to talk about another one, another micro to meso model, but in the context of inference. So we're going to infer the mesoscopic population model from the spike trains of a population of neurons. This is work done by Alexandre René, PhD student of mine, who's co-supervised by Jacob Macke, who's now in Munich. And the idea is you have microscopic data, for example, individual spike times, or it could be fluorescence data, it could be optogenetic data from many different cells in different populations, and you want to use these data to construct population responses. And you want to find a theory that models population responses at the mesoscopic level. So for example, the Wilson-Cowan or the SRM, or the one I just talked about with Guéry and Alexandre, or the one I'm going to talk about now. We ended up using the one by Thilo Schwalger. And you want to get that theory that gives you the mesoscopic description as a function of the microscopic responses. And you can use that mesoscopic model to do the inference. So you must be able to write a likelihood of observed activities and use this likelihood to fit the parameters of the mesoscopic model. And you can add adaptation or other phenomena of interest as long as you can do the theory for it and have a mesoscopic theory. And so that's coming out in the next month or so in neural computation. So to summarize, you have a microscopic model with excitation and inhibition. We have adaptation in our case, and there's going to be escape noise again, so a hazard function. So we're not dealing with stochastic differential equations. We're dealing with the SRM formulation, which is perfectly fine for this. And from this, there's analytic work that gives you the mesoscopic model. In parallel, you can also simulate the microscopic model and then concatenate these data to produce the summed activity. And the summed activity is what's going to be used to fit the mesoscopic model. Does that make sense? Right. I'm not going to go through this, but this is a diagram of the model by Thilo Schwalger and company, where you have inputs down here, neurons that have recovered from refractoriness, neurons that have not recovered from refractoriness. So there's a finite memory to the refractoriness. You have finite size effect corrections, and finally you get these outputs, which are these binomial variables at each time step, number of spikes fired. They give you the activity. That's in a nutshell what's going on. The equations again is the SRM formalism, but we're using generalized integrate and fire, and we have leaky integration, adapting threshold, and escape rate process. This is all in Thilo's model. So the spike trains are these delta function sequences. You have the synaptic responses, which are exponential. You have the sum of the synaptic inputs. There's an alpha here, which always refers to different populations. The potentials of the different neurons, the threshold dynamics, and the escape rate, the hazard rate. So you have number of neurons, number of populations, number of time steps to compute the likelihood function. And there's going to be, the neurons are going to be 1. So this variable is 1 if the neuron fires, 0 otherwise. And this is the activity, and this is the expected activity. So we call it a meso-GIF model. So for a data sequence of length L, and finite history S, and a starting time K0, that sequence has probability, which is the product of all the probabilities over time and across the populations. And then you take the likelihood of this and you substitute binomial statistics for these P's. And what we did is, so this is all in Thiele's model. So what we did is apply stochastic gradient descent on this to fit the parameters. We have a 2 population model and a 4 population model. Those are both in Thiele's paper as well. So we have we're not estimating all the parameters because that's too many, and some of them are degenerate anyways. You wouldn't want to estimate all of them. But we're going to look at a situation where you estimate 14 for 2 populations, which is an EI network, and 36 when you have 4 populations. So here's how it works. You go from, so you can train the model, and you can train it on sinusoidal input. This is the sinusoidal input. It's actually a multiplicative noise here on the input, or a stimulus-coded noise. You get these spike trains, and this is the sum activity, and this is what you feed into the algorithm. Then you run, for example, 25 fits, and you keep the one with the highest likelihood. So the gray ones go all over the place. For example, parameter connectivity IE as a function of iterations. And you'll see, and the black is the ground truth. Okay, that's the real value, but it's not the real value of the microscopic model. It's the real value of the mesoscopic model using the parameters, the real parameters of the microscopic model. So micro parameters give you a meso parameter, and you're fitting your parameters and looking at the quality of the fit compared to that ground truth. And you'll see one here is getting close to that ground truth. The red one is the best one. And we keep that best one for each. Then you can test the ability to generalize. For example, you can test it on low-pass filter noise. And it turns out that even just a bit of fluctuations around the steady state are enough to sometimes even to fit the model. But we're giving it a bit more transient, like a longer time scale of a sinus input to help the model train and explore more of its space. So what we can compare is the true microscopic, the green. I'm going to look at the blow up here. And then there's the theory based on that true microscopic, which is Thiele's theory, which is the orange, which does amazingly well. And then the blue is the inferred from the technique that we developed. And the blue is also following very well in this whole trace. What you can do is also calculate the Pearson correlation coefficient between the different trajectories, or the root mean square error between them, and see how you're doing. Turns out that convergence was good for this class of model with these parameters after about 20,000 spikes. So this is in the neighborhood of, it's not gamma activity, it's asynchronous activity. But you notice here as you're going from top to bottom that the agreement between the true meso and the inferred model gets better and better after about 9 seconds. And 9 seconds is about 20,000 spikes. So you can plot these quantities, for example, the Pearson correlation coefficient as a function of time, and you're going to reach some plateau. You can have the single trial one or the trial averaged one. It doesn't really matter. They have slightly different information, but you can get there within about 20,000 spikes. Now here's an interesting observation. I'm going to wrap up in about 5 minutes here. We can throw at this model some heterogeneous population, because so far we were talking only about a homogeneous population. Now, there can be many populations, but within each population, it's homogeneous. And the theory that Thiele developed is actually for homogeneous networks. It can accommodate some heterogeneity, but it's basically homogeneous. So in this case, we have 3 time constants, which instead of being the same for every neuron, they're log normally distributed. So for example, the adaptation time constant for the excitatory cells, the membrane time constant for the E and the I cells. Those are the three, okay? So the true micro activity is this. This is in response to a step input. At the end here is the result of our fitting with so if you do the inference on the data from the micro, you get something that actually matches pretty well the data. Whoops. But notice what happens is our tendency is often to take the average parameter. If you know that some parameter is heterogeneous, you would just take the average of that parameter and see how you're doing. Now, of course, that's not a really good idea to do if the distribution is log normal, but you get the point that if you take the average of things and you plug that into the mesotheory, it doesn't work so well. But if you take the inferred parameters and plug them in the mesotheory, it actually works pretty well. So the inference technique is kind of is able to approximate a model mismatch, if you want, because you don't have the right model. The model assumes homogeneity, but the inference has some flexibility to go explore and compensate for the model mismatch. Okay. This is a detailed version of this. So these are the three distributions of the parameters. And these are the responses if you use the mean parameters. But what we're doing here is actually illustrating another point, is what happens if you look at the inferred result if you fit only two parameters. The membrane time constants, two of them, actually three parameters, the two membrane time constants for the E and I cells and the adaptation current for the E cells. There's no I adaptation in this model. And you're doing better than with the mean parameters. But actually, if you infer all the parameters at once, you are not so constrained by having just those three parameters. You can explore more freely, and the error goes down, the correlation goes up. So the moral of this story is that fitting more parameters, 14 parameters when you infer them all versus 3 parameters, certainly takes more time, but you have more opportunities to accommodate the model mismatch. And a final interesting point is that the Bayesian inference, of course, can give you good fits, but it can also help you characterize the parameter uncertainty and the correlation. So what you can do is with your map estimates, with your posterior distributions, you can do Monte Carlo sampling. And we did Hamiltonian Monte Carlo sampling to get these joint distributions of 2 parameters at once. Of course, this is 14 by 14. You can look at all the 14 by 14 matrix, but these are 2 elements of that matrix. And you notice that some parameters, it's kind of around, these are Gaussian fits to the distributions here of the likelihood. And you find that they're not, these are pretty symmetric. So there's no correlations between these 2 parameters. In this case, the J and the WEE. But over here, between the W, so for example, this one here, tau M and WII, there actually is some negative correlation that's pretty strong. So you can pick out with this inference model what parameters are really dependent on one another. So if you move one up, you have to compensate by moving the other one down. It goes in the other direction as well. So for example, the threshold characteristic here and the connectivity strength also covary in the same way. And actually these ellipses are very tight. So this makes for some pretty fine tuning of these parameters. They will kind of tightly follow each other. So that's something you can get from this formalism. And finally, I'm going to just show you, a 4 population model, which is also done in Schwalger et al.'s paper. 36 free parameters. This is the model published in Cerebral Cortex by Pojans and Marcus Diesman. And we tried to infer that. So Thilo showed that he was able to get the simulations to agree with that, with their model. And the inference actually gives you something pretty well. So we're able to infer, we train with a sign input only to layer 4. And the fluctuations in the other layers are enough to help the inference of all the 36 parameters. And you can get pretty good results. Challenges, what if the model is incorrect? Then you're getting some effective description, but how good is that? That's a very big open question. What if we have only partial information? What if we don't have access to all the E and I populations in your diagram? What then? And can you do any of this online during experiment to calibrate, to modify things, or during surgery, even better? So that's it for what I wanted to show you. And that's it. That's where I'm at right now. For delay.
Okay.
Putting into here.
Don't make it. Oh. No. We'll see what they say.
I have a question, Andre.
Yep.
Yeah, really cool stuff. Always a mountain of research here. So in your second story, where you did the finite size corrections, sort of similar to what Vincent and Nicolas did in their 99 paper, but I'm trying to get an understanding of sort of where the core differences are between sort of their approximation that was sort of just for this, they just put a noise term in the Fokker-Planck equation, and then they got sort of they now looked at the autocorrelation function of the population activity, and that allowed it to sort of have finite memory, especially when you're past the hop, when the system's in the oscillatory regime, right? Then in principle, if there's no noise, your autocorrelation just goes on forever, right? But then with noise, this decays quickly. You showed theory and simulation matches on the side of the hop where the limit cycle didn't exist. And then your last one you showed, it was on the other side in the limit cycle regime, right? I remember there was three examples, but I didn't see red there. Do you have theory to match in that regime?
So let me go back.
Yeah, it was in the second part of the talk when you were sort of straddling that hop with 3 parameter sets.
Yeah.
Yeah, there you go. That was
so here you have the theory actually runs into problems there.
I bet. Yeah, that's a hard regime. Yeah, I was just curious to see if you got it there too, but okay.
Yeah, but the SPD actually accounts for the spiking network activity. The more general question of the differences in so what Nicolas and Vincent did was a single effective neuron approximations, or Fokker-Planck equation for and calculating the fluxes of that. And I think that also captures a lot of the fluctuations going on in the problem. So and they can put a delay in there as well.
Right.
Here we have the we have the whole SRM formalism, which has basically the same kinds of parameters. And I don't think I have a clear answer on the advantages of this compared to their method for getting the correlations. You do get a very quick method to simulate the whole network out of working on the discretization along a characteristic curve. So let me leave it at that. And but that's still to be pinned down.
But was this with delays too? You have delays in this?
Yes.
Okay, cool. All right, nice. Thanks.
Horacio?
Yes, Andre, thank you. It was a very nice talk. How are you? I have a quick question. Perhaps it's lack of understanding, but is there any chance that during the inference process you capture parameter values that are not the ones that are the realistic ones? So in other words, if you use a ground truth model with certain parameters, is it possible to capture different parameters, given the possibility that you have certain degree of unidentifiability in the models?
The likelihood function is certainly non-convex. And you look at this plot here, you see trajectories going a bit everywhere. We just found that if you run this a number of times, you will find an optimal likelihood. But I guess you're asking is, could you discover other combinations that would work?
Right. It's another word. Yeah, exactly.
And the answer is yes.
Markers, etc.
Yeah, and for the examples that we've looked at, we haven't come into a situation where we have close runner-ups, but you could imagine some parameter sets for some networks where you could have different parameter sets that are competing with similar likelihood, just not in our case here. For the ones we've shown, it's always pretty clear. But it would be interesting. Then you'd have some degeneracy.
Exactly, yeah. So perhaps we can talk more about that by email. Thank you.
Okay, nice seeing you.
Hi, it's Alec again. About these tonic and phasic activities, I want to ask you. The models you describe, it's for phasic activity, as a description, I believe, when none is there, and then suddenly, depending on model, you have bursting. You think there can be same time tonic or continuous activity as well?
I'm not sure I understand the question. Whether you can have tonic activity.
Let's say continuous gamma oscillations can exist as well, yes? But
are you talking about the inference or the modeling of the gammas themselves?
Let's say gamma oscillation himself, but gamma oscillation can be as continuous something, continuous activity.
Yes.
Or it can come as bursting activity.
Yes.
Your model describe bursting mode of working only, or let's say you have both same time. Let's say you have continuous gamma oscillations.
I understand.
Time to time, something happen in the system, and you have increase of, let's say, that same oscillations in form of as burst.
Yes, I would. That's an interesting question as well. What you have is stationary statistics for the models that I've shown, right? These differential equations here are, just stationary processes. They'll have a certain burst distribution, burst durations, distribution of time between bursts. That is fixed for the parameter that you chose. If you're working, for example, here or here. What you're talking about, of course, arises also in the data where you can have like longer stretches and there's more non-stationarity going on where the statistics are changing. You would have to incorporate more biophysical information in the model, such as some kind of neuromodulation, which in principle is possible to do. You would have another slow variable in there, and you can do the stochastic averaging method on that as well.
But it's important, let's say, to see if mechanisms of generating this oscillation are common or for continuous activity or bursting activity, or they are totally different.
Absolutely. And in the context of, let's say, Wilson-Cowan picture or the Brunel-Hakim picture, those are not going to give you that. They're going to give you, as far as we know, you're going to get, these kinds of phenomena. Now, I would see it maybe, if you're near some kind of crisis and chaotic attractors, laminar chaos, for example, you'll get long stretches followed by short stretches that seem to have different statistics. If you simulate long enough, it's of course stationary.
Yes.
But on a finite time scale, it might actually look non-stationary just because you have these saddle points and you're going in and out of laminar regimes, and that might well be going on as well. That's an interesting question.
Thank you.
I think there was one more question.
Hello, this is Huilin. I'm quite interested in you mentioned that you may be able to inform how to interrupt the pathological oscillations like using DBS in Parkinson's disease. Is it possible for you to give any bit more details on that?
So let's say I don't know the details yet about, I can't remember the details, but I know in Parkinson's disease, you have these, they do experiments on patients for like stop signals and start signals, and the burst statistics.
Yeah, they found that, I think they found that in Parkinson's disease, they tend to have prolonged burst.
That's right.
When they're off. So the idea is to cut short those bursts.
You need to cut short, and there's some kind of control mechanism maybe arising from prefrontal cortex that's going to change the statistics and shorten them. In our case, you know, like this rudimentary theory would tell you, if you want to shorten the burst statistics, move away from this boundary. This is only two-dimensional subspace, but whatever you do, try to move away from this boundary. It's very reminiscent to what happens at a Hopf bifurcation in general, or any bifurcation, is that you get very long correlations. You lose, you know, linear stability. So if you want to reestablish maybe short burst statistics, in this case, you move away from these bifurcation boundaries. How you move away, I was talking about this with John Rubin about a year ago. He thought, you know, maybe a basic model for beta is actually, you know, you get rid of the EE connections, if I remember properly, or, but you know, it's the subthalamic nuclei literature is pretty intense, and I won't pretend to know it too well, but I know that, you know, if you have an idea in mind that there's maybe less excitation, then maybe you would move away from this boundary, less E to E connection, you move away from this boundary, and that would give you shorter bursts. So that would be in line. You know, so maybe the pathology is when you get too close to here and you need to move back here. But again, this is a Wilson-Cohen EI network, mainly for gamma oscillations, not beta. But that would be the let's say the way to think about using these envelope models in the context of Parkinson's, is how do you change the statistics by changing the biophysical parameters. And of course, you can try pulsing the thing as well, which, you know, we're not doing yet.
Thank you.
You're welcome.
I see currently no other open mics. If you do have questions, come forward now, or if you want to stay for a one-on-one with Andre, just stay until after this is over. And since we do have no other questions, thank you very much again, Andre, and talk to you soon, and see you soon again.
Okay, thank you, everybody. Thank you.